Hey friends, it's Ben again. This is a video for the differential equations class. It's a little off of the beaten track. It's really meant to respond to a couple of questions that I've gotten again and again, okay? So the two questions are really about the linear equations that we're dealing with, linear homogeneous equations. So the thing that I want to say something about first is about the whole notion of the sine and cosine and how that fits in with solving for R. So let me do a quick little example here, and this is not going to be too sophisticated and hopefully not too complicated. All right, so as we had seen before, if you're okay with just taking the answer that when you get an R turning out to be an imaginary number, that you just put your answers in the sine and cosine form, then go ahead and take it that way. But some folks felt like this just kind of felt weird. So I am going to look at this specific one here of y double prime plus y equals 0, okay? And we are making this supposition and guessing that the answer is of the form e to the rt, which says that y prime is r e to the rt. It says y double prime is r squared e to the rt, because every time you take a derivative of e to the rt, you just get another term of r's out there. So that means we have an r squared e to the rt plus an e to the rt equals 0. And if we factor out the e to the rt, we have r squared plus 1, and the whole thing equal to 0. Well, of course, e to the rt can never be 0, so we can just divide by it. And our r is plus or minus I. So if you had another complex number that had a non-zero real part, then you would see the exponentials cropping up a little bit more here. But I wanted to just do this quick, simple example because I have said to y'all that your general solution here would be y equals a cosine t plus b sine t. And that feels like it doesn't fit with what we've been doing otherwise, which would be y equals a times e to the, first one was positive it, and then the second one was negative it, all right? So what I want to do is to just extend this example a little bit and show you that it really doesn't matter which way you go on these, and the first one is usually easier, okay? So what I'm going to do is to take y of 0 equal 1 and y prime of 0 equals negative 1. Those could have been any numbers at all. I often pick ones where the arithmetic is easy, but that's all that's going on here, okay? Pick any numbers that you want, and you can do the exact same thing that I'm doing, right? So I'm going to go ahead with the solution that has the exponentials in it and solve that out, all right? To do that, I'm going to need y prime equals ai e to the it minus bi e to the minus it, okay? All that was just taking the derivative because I knew that I had to plug in. So y of 0, plugging in there, you'll get an a times 1 plus a b times 1. And we know that that's supposed to equal 1. Then your y prime of 0, when you plug in there, you'll get an ai minus a bi, and that's supposed to equal to negative 1. So with trying to solve a system of two equations, two unknowns, you can do it by elimination or you can do it by substitution. I usually do elimination, so I'm going to do substitution this time. So I know that a has to be 1 minus b, and so when I replace it in here, I can see that I end up with 1 minus 2bi equals -1. Then I'm going to divide both sides by I. And when I do that, of course, I have 1 minus 2b equals, let's see, -1 over I will turn out to be the same as positive I. Okay. And so that means that my b is going to have to be 1 minus I over 2. I did a little bit of that in my head, but you know. Then the a, we will just plug it back into this equation we had here and find out that the a needs to be 1 plus I over 2. Okay? So once you have those, we'll plug back in y equals quantity 1 minus I over 2 e to the it plus amp plus goes here. This one's the minus over 2 e to the minus it. Okay. And now I'm going to expand out my e to the it using the Euler formula. So just leave this here and have cosine t plus I sine t. All right. And the other one has 1 minus I over 2 and cosine t. It turns out to be minus I sine t, because when you plug minus t into sine, because it's an odd function, you would end up getting minus sine t. All right. So I'm just expanding out here, and I'll have in the first one a 1/2 cosine t and a 1/2 I sine t, and then plus 1/2 I cosine t, and a minus, now let me write plus I squared, and I don't like the way that looks. So plus 1/2 I squared sine t there at the end. That's just the first term, okay? And we're going to go back and fix this here in a second. The other piece is plus 1/2 cosine t and minus 1/2 I sine t, and then minus, is that right? Yeah, minus 1/2 I cosine t, and then minus a negative, and I forgot my 1/2 again, 1/2 I squared sine t. So I wrote those the way I did so that you could see those canceling out. Now I have 1 cosine t minus, because the I squared is really -1, minus 1 sine t. So if you have real valued initial conditions like we did here, and you work with the complex solutions but simplify it, the answer you eventually come down to, you could have gotten, why on earth does this keep appearing here? You could have gotten it all by just saying y equals a cosine t plus b sine t. And it actually would have been just a little bit easier, okay? So that's just a quick example. It isn't exhaustive, but the thing that you'll find is that the initial conditions you get for A and B on the two conjugate roots there are going to end up being coefficients that are conjugates to each other, and they cancel out the imaginary parts. And it's going to work like that every time, okay? So there wasn't anything magical about the conditions I chose. It was just something where the algebra wouldn't be too awful, okay? So then the other thing that's coming up is that people are making the observation that the t squared, y double prime, and ty prime, and then y equations, the equidimensional equations, they feel like they're way different. And again, I've tried to just tackle things by giving you the easy way to get a solution on it. But let's take a quick look at this. And this time I have it written ahead of time because some of it is a little bit of a pain to write. So this here, I'm going to just talk about how to do a transformation and see that these are really the same thing but hidden, okay? So the method that I gave you all to do before on these is that we're just going to make the guess that y equals t to the r is going to be the solution on these. And once you've got y being t to the r, you know that y prime needs to be r, t to the r minus 1, and y double prime needs to be r minus 1, t to the r minus 2. And then if you multiply this one by t squared, then you'll have a t to the r, and this one by t, you'll have a t to the r. And so we can cancel out a factor of t to the r through the whole thing because they'll all have a factor of t to the r. But you have to keep in mind that t cannot be 0, okay? So with doing that kind of technique, it turns you into an equation that I use the term characteristic equation just to make it distinct from the initial equation. And that gave you something that you could work fairly easily. I was able to factor these out, and I got my two solutions, y equals a t to the 6th and b t to the minus 2, right? So perfectly valid way to go, and that gets you your solution. Now I want to connect this up and show you that this transformation here is going to let you actually solve this differential equation as though it were a constant coefficient differential equation. But remembering that we had said we will not have t being equal to 0, then it's okay for us to have x equal log t, which also will not allow t to be equal to 0. And that lets us make this change, that just when you reverse things there. And so if I need to talk about t squared or t to the minus 1, I'll just put a coefficient in front of the x on the e to the x, okay? So here's the hard part. When you want to transform your differential equation, you are going to have dy dt, that y prime, you need it written as a derivative of x, not t. So the thing that I do here is to look at the chain rule, which says that if you're going to get dy dt, you could get it by going dy dx times dx dt. And because we have x in terms of t, that means that you can take the derivative of x with respect to t. Since it's log t, then you get just a 1 over t. But we want our final solution not to have any t's in it. It needs to just have x's. So that's why we get this dy dx e to the minus x, okay? Now, I said that was the hard part and I lied, because in the next step, we do the really hard part, which is getting the second derivative, okay? The thing that we've labeled y double prime above. So we know that d squared y dt squared is really the derivative with respect to t of dy dt. And we'd already figured out dy dt in terms of x, which is kind of unfortunate here because now we have to take a derivative with respect to t of something that has just x's in it. Yeah, okay. But in heading there, I'm going to go ahead and note that there is a product. So I'm going to break this into two pieces, and I'm going to apply the product rule and take the derivative of the first part, leaving the second alone, And then I'm going to take the derivative of the second part, leaving the first alone. So when I do that, then I, for the first one here, can say something about taking the derivative of dy dx with respect to x. So that's the second derivative with respect to x. But then I pick up this dx dt term, okay? And if you look further on, dx dt was just 1 over t. So that's going to turn into an e to the minus x, and that's why we have this e to the minus 2x cropping up here. On the other factor, though, we were having to take just the derivative with respect to t of e to the minus x, which was just the derivative of 1 over t with respect to t, which of course is going to be negative 1 over t squared, which is e to the minus 2x, okay? And the minus of it, notice that I went ahead and just moved it over here, okay? But in any case, you notice that I've got a factor of e to the minus 2x on both of those. So I just pull it out to the front, and now I have second derivative with respect to x minus dy dx. So when I go back to the original equation, I need to substitute that mess in for this second derivative with respect to t. So my t squared becomes e to the 2x, and my second derivative becomes this stuff. And then I have to have minus 3t, which will be minus 3 e to the x. And the dy dx we said was, I'm sorry, the dy dt was dy dx times e to the minus x. And then as a last little bit here, the minus 12y, which is just going to be minus 12y, okay? But notice we had an e to the 2x and an e to the minus 2x. We had an e to the x and an e to the minus x. And that means that this little bit here can just be written out there. And then my minus 3 dy dx comes down, and my minus 12y comes down. So when I combine it together, I end up getting my second derivative with respect to x, and minus 4 dy dx minus 12y. And we are trying to change this and have y equals e to the rx be our guess here, okay? And when we do that, which we can because it has constant coefficients, we get the same equation that we saw before. And we solve and get the r equals 6 and the r equals negative 2. Well, that tells us that our y is going to be a e to the 6x plus b e to the minus 2x. And that's nice because e to the 6x is really e to the x and then to the 6th power. But this e to the x was t. Same thing with the other part there. So we end up getting the same solution when we transform it back as a function of t. And this transform of getting the ln(t) showing up there is the reason why if you have a higher multiplicity solution that you multiply by powers of log t rather than multiplying by more t's. So hopefully that gave some motivation for why we have extra stuff popping up there. But it also gives a connection here that all of the stuff that we're doing with the linear equations, both the constant coefficient and the equidimensional ones, it's kind of the same thing. We are making a guess and then using algebra to say which of the functions we guess might be a solution are the correct ones. So, and algebra is easier than differential equations, right? So, all right, hopefully that was helpful. Let me know. I've watched enough YouTube videos now that I want to tell you, let me know in the comments, but yeah. let me know in person.